Here we go. Question 5, component 1. In-class questions. As you see, I've got my scientific calculator. I'm going to pretend to be a scientist today. Right, bacterial growth curve. It looks a bit angular, but you can sort of see the shape that you're expecting. And this is E. coli. And it tells us something about the generation times the time for the cells to divide. And we measured this over a 20-hour period. We have got time on the bottom in hours. That will provide some confusion in a bit. And definitely a source of confusion up the side. Number of cells. We've got this kind of a crazy log scale there. And they do this because the amount of graph paper that you would need if you were using a normal scale would go off the page and into next door. So we're using a log scale where each division is a factor of 10. I could possibly translate these numbers into English, and anything to the power of 0 is 1, so that's 10 to the 0 is 1, 10 to the 1 is 10, 10 to the 2 is 100, and so on. So 10 to the 3 will be 1000, 10 to the 4 is 10,000. So we just keep adding a 0 on each time, and that's how they are. That's how you can interpret that scale, and you can keep going. 10 to the 6 would be a million, and so on. So we've translated that scale into numbers that you're used to. Use the equation below, a frightening statement, to calculate the generation time. Give your answer to the nearest minute. Right, we've got minutes in here, and we've got hours on the graph, so we're going to have to factor that in. So equals, let's just write the equation out. T, well, the time interval in minutes, so we've got on our graph between 4 and 8 hours. Where are they? So if I highlight where 4 hours is and then where 8 hours is, they conveniently are placed in nice places on the scale there. So this would be 10 to the 1. So 4 to 8 hours, so that's 4 hours, and how many minutes is that? Well, times by 60, so 4 times by 60, you can do this in your head, 240, so that's going to be, I'll write this out, so 4 hours equals 240 minutes, so 4. Then we've got some shenanigans underneath. So we've got log of little b. Little b is number of bacteria at the end. So at the end of the time interval, that was 8. That's 8 hours. Number of bacteria is 10 to the 4, or 10,000. So that is log of 10 to the 4, or 10,000. And underneath is big B, so that's at the beginning, so that's 4 hours, so that's 10 to the 1 or 10, so that's log of 10 to the 1 or 10. So how do we do logs on our calculator? Well, I've just spent about 10 minutes trying to figure it out, so I can now do that. 10 to the 4, that was 10,000, so log 10,000 equals 4. So this is going to look like 3.3 and 4 divided by log of 10 here we are, we get log of 10 is 1. So we've got that'll be 3.3 times by 4. So 3.3 times by 4, 13.2. So that's going to be 240 at the top. 240. 240 divided by 13.2. 18.18. 18.18 minutes. And that's our answer. It's just putting the stuff into the equation, figuring out what logs are. You didn't actually need the calculator. You didn't need the calculator to work out the logs. So if you know what logs are, log of 10 to the 4 is just 4. So maybe you need to brush up on your logs. A lot of work for 3 marks there. But I would only get 2 marks, wouldn't I? Because, what does it say? Answer the question. Give your answer to the nearest minute. So the nearest minute would be 18 minutes. So I can now have 3 marks for that. Amazing. If you did all that work and then missed a mark off because you can't get it to the nearest minute. Read the question, answer the question. The scientists carried out the experiment again, but counted the living bacteria present each hour for 60 hours. So we're now going on this scale for 60 hours. Describe and explain the expected shape of the curve between 20 and 60. So we can imagine there's going to be 1 mark for describing and 1 mark for explaining here. The curve already is flat at the top from 16 hours. So it's going to be flat, and then the curve would probably start to decline in the classic shape from your notes. So all we need to do is describe, the line would start to decrease, and that's the death phase that we're describing there. And we need the bit of the biology. Well, in this batch culture, then our nutrients are going to run out, and possibly toxins are going to build up, and that will lead to the death of cells. So we can say nutrients, for example, glucose, or whichever sugar it mentions, will run out. Or we could possibly say there's a build up of toxins. So pretty straightforward 2 marks there after the car crash of the equation earlier. And B2, explain how it would differ if the total count had been used to measure the population density and suggested disadvantage. So another really typical question. If you've done plenty of practice questions, you'll know your way around these 2 marks. So in the total count, dead cells are included, because you're just essentially looking down a microscope at them and counting them quite often, and you can't tell which ones are living or dead. So dead cells are counted. What would that do to the count? It wouldn't decline like we've just mentioned. It would stay at the same level, because we would just keep counting more and more dead cells. The count would stay constant. And we need to suggest a disadvantage of this technique. Well, we wouldn't know. We've just been talking about the death phase, but we wouldn't know when the death phase was if it's just constant. So we wouldn't know if these the problems are building up. So the death phase cannot be identified. So in these questions, I mean, there's quite that last mark is a little bit difficult to think of, but if you're stuck for things to think of, just go, what has it mentioned already in the question? B1, what was that about? And use that to answer B2. So if you're not sure, always go back and have a look at what it was chatting about. Can I mention that in any way possible?